I hope everybody had a great Thanksgiving. I hope you guys did some sort of homework for some of your classes over Thanksgiving. It didn't just go brain dead for 6 days, 5 days, because you got less than 2 weeks left for the semester. Let's finish strong. Today we're doing 15.7. It's on the divergence theorem. And we have the formula for the divergence theorem at the top without listing what the limits of integration are, because it's dependent on how we're going to set it up. The left side, if you've been working on your homework, this was flux. So we can calculate the flux as a triple integral rather than doing a double integral. Rather than looking at what goes through the boundary of a solid, we look at the divergence of the vector field over the solid. Which can be very, very handy, especially for surfaces that are broken up. I know in 15.6, much to many students' annoyance, I know Lawrence and Carlos were like, WTF. One of the problems gave you a cube and told you to do the shit over the cube on each side. You had 6 integrals to do. That's a pain in the ass. Well, rather than doing 6 sides for the using the divergence formula, you just got 1 integral. So divergence formula can save a lot of time. And we'll do both sides. I don't know which side you want to do first. There's a lot of ways we can even tackle the flux, because we're looking at a sphere, right? So one way would be to shift to spherical coordinates. We could do cylindrical coordinates. I don't know how do you guys want to do this? Because this is a sphere where rho equals 1. So one way, if we wanted to do rho equals 1, we could do spherical coordinates where we're just, since it's rho, phi, and theta, And rho is a constant. We're down to 2 coordinates right there. If we called like phi, said u is phi and v is theta, we could do ru cross rv. So we got to parameterize it in terms of r. So if I did that, if I did r of rho, theta, and phi, the x component, the radius is 1, so we leave that. We don't need to put rho in. We have cosine theta sine phi. Let me do it below. Cosine theta sine phi for the x component. And since rho equals 1, y is sine theta sine phi. And z is rho cosine phi, and rho is 1, so z should be cosine phi. And the only reason I listed u and v is because remember, when that's the way we wrote it, is one of the ways of doing this is ru cross rv. So I'm going to do like r phi cross r theta. So maybe we need to figure out what those are. So r of phi derivative of sine is cosine. So this is cosine theta cosine phi. Sine theta cosine phi. And negative sine phi. And I'll put commas in there because this is a vector. R theta, we have negative sine theta sine phi. We have cosine theta sine phi. And we have 0. And we want to do the cross product, so I'll set up a little matrix here and calculate it out. Zero minus that is plus cosine theta sine squared phi. And we're doing the j, that minus that. Those two negatives cancel, so there's a minus, and then j is negative, so that'll be positive. You've got sine theta sine squared phi. And what is the k component? K component is going to be a little more work. So we've got cosine squared theta cosine phi sine phi plus sine squared theta cosine phi sine phi. And if we factor out the cosine phi, sine phi on both, we're left with cosine squared plus sine squared, which is 1. Which means the k component simplifies down to the cosine phi, sine phi. Pause for a second, let that sink in. All right, so we have f dotted with that. Which means we've got what, 5 sine phi or sine theta, sine squared phi, plus 7 cosine phi, sine phi. And we're going from 0 to pi and 0 to 2 pi. Give that a little bit more room over here. D phi, d theta. Since I didn't start with any my integral in dx dy, I went straight to spherical with using the RU and RV. We don't need to do the rho square sine phi. We're already in the right system. Pain in the butt though already, isn't it? This is a lot of work. Let's see. So if I do 2 integrals on the left one, I never remember what it is, so I have to write it out. I want to change the sine squared into like cosine 2 theta. So cosine 2 theta, do it down here, is 1 minus 2 sine squared theta. Maybe I'll put phi so I don't fucking forget. So if I solve for sine squared phi, I've got -1 and then divided by -2. I've got sine squared phi is 1 minus or 1/2 times 1 minus cosine 2 phi. So the integral on the left is 0 to 2 pi. I'll do 5 halves, put the 5 and the 1/2 together. 5 halves sine of theta 1 minus cosine 2 phi. And that's d phi d theta still. And the right side is, we've got plus.
Oh,
And
you missed the balance. You only put
You're right,
the.
I did. I only got one there, don't I? Good catch. Here we'll do a U. Let's do a U sub. So U equals sine phi. Du is cosine phi d phi. Well, thank you for being annoying, McAfee.
I wasn't sure if that was my screen or your screen. It's Cyber Monday.
And when we plug in 0, when phi is 0, U is 0. And when phi is pi, U is 0 also. Which means we are going from 0 to 0, and that entire integral ends up going to 0.
For your U sub, that's sine theta, right?
That's,
Yeah.
sine phi.
Sine phi. I'm doing
Sine
this one
phi.
right here, so it's sine phi.
Oh, okay.
So that integral goes to 0. We've got 0 to 0 on the limits of integration. That just cancels out. We got nothing. But I will write it since we're going to the next tab. What we would have 7 U du d theta. And this will go to 0. All right, pause for a second, because we're going to need the next another. This problem is taking a lot longer than I had anticipated for doing one problem. Because we haven't even hit the divergent side. Divergent side should be quicker.
I sure love it when the one was my class take half the class. Because trust me, I'm not doing this.
All right, so actually we're about done, because this other integral, this goes to 0. This other integral is separable now. And this one might have an answer, but the left side, we're going from 0 to 2 pi on sine. This goes to 0 also. So who gives a shit about this one?
Who cares?
So our entire process, F dot NDS, resulted in 0.
I love calculus. It just be doing that. Spend 30 minutes on a problem just to get 0.
You should just said it was 0. That looks like it'll be 0.
When you have 0 to 2 pi, it's a periodic function. So we're back to where we started. So sine theta valued at 0 and 2 pi. When we shift it to cosine 0 and cosine 2 pi are the same value. You're subtracting, you get 0. That's the joy of we're doing integrals on periodic functions. So the entire long drawn out process for doing the flux was 0. I'm going to rewrite what we had, and then we'll do the surface, or we'll do the divergent side.
Is it a univector? I forget these are the-
You look at the soil note and then it's the normal, so it's.
You normalize the, is it already normalized? Is the
The
Oh.
F vector?
the n vector, yeah.
Oh, the in vector.
What?
The
Are you guys ready for the next part?
cross the.
Do we have a question?
And did he normalize it?
You mean like he found the
Doesn't- doesn't it
univector
need
of
to be-
it?
Doesn't it need to be a univector?
No,
I-
when you end up doing it this way with F dotted with RU cross RV. Let me put this up here and discuss it. And you've got du dv. When you do the du dv, you also have the Jacobian in there. Du dv. And that part of the Jacobian cancels out with the norm. This part is on top and this part is on bottom and they cancel each other. So when we do F dot RU cross RV, we do not need to normalize it. It shows up in the formula already. All right, so let's do the divergent side. We know the left-hand side is 0. The right-hand side should be 0. We are doing the divergence of F dv. And this is the really, 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 really super fucking quick one if you're paying attention. You might be so inclined to try to take the divergence of the surface, which you can't, it's not a vector, but you may think that. But really, it's the divergence of F. ddx, ddy, ddz, dotted with 0, 5, and 7. There are no variables in F, so the divergence is 0. That's div F. So we got the triple integral of 0 dv is 0.
And then the normal, and this is- Wait a second. That's a constant.
It's some constant, but that some constant is definitely 0.
Be like,
That's what we're saying. The constant is 0. Let me actually thinking about it. Let me think. So, Mr. Jones, just to satisfy Lawrence here, because he's skeptical as usual. Would there actually be a point where in this situation that it would not turn to be 0, but instead some constant c?
No, because we are talking about the flow through something. And kind of like having a constant, the only way to not have the so we're doing the flux through this sphere. So there's flow through it. There's no x component. The flow is going one way. So what goes in the sphere goes out the sphere. The only way this is not 0 is like, say it's 1, means there's more going in than coming. There's more going out than coming in. But the flow is constant. The flow is constant, so there's no way there's more going out than in.
0, I don't think 0 means.
So it's got to be 0.
0 is just in and out the same rate.
Yeah, well, that's what he's saying. The
Flow
F
in
vector,
equals
that we
flow
have,
out.
yeah.
There's no
the
source
that we have,
inside,
so,
no source or sink inside. Because the flow is constant. So the flux has got to be 0. That's your physical interpretation of it. Yay for physics.
there you go, Lawrence. You got your physics for the day. Well, you got your physics on this class of the day.
It's a good question, though. And another reason that you may like that's more mathematically based is this was 0, 0, 0 dV, but if I put any limits of integration on it,
It's not going to do anything to it.
when I put limits of integration on it, it cancels out.
Yeah,
Every single integral is going to have f of b minus f of a, and every single one of those is going to be c minus c equals 0. And so every time you do one of the integrals, you're still left with 0 inside. Because this is not an indefinite integral. It's a definite integral. So that's the math jargon approach to it. The flux, I think, is a handier interpretation to get the picture of what's going on, but that backs up the math part. You guys ready for another?
Oh, yeah.
On this
Oh,
one,
yeah.
well, let's just use the divergence theorem. We don't need to do both sides. So let's use the divergence theorem. Because let's face it, that left side was a lot of work, wasn't it? And it almost always is for the divergence theorem. The flux is always harder to do than the boundary or the solid. Very rarely is it the other way. So it's a good idea to have a sketch of what's going on here. And Lawrence was asking me about a problem that was very similar to this just yesterday, I believe. And I quickly said this was a cut going downward. And he said, how do you know that? Well, when we're sketching it, I like to do it in terms of like, let's do y equals 0. When y equals 0, I have z equals 1 minus x squared, which is a downward parabola like that, with that being x and that being z. And if I do the same thing with x equals 0, I got z equals 1 minus y squared, which makes it the same graph if I change that to a y. So in the zx plane, I can do that just fine right there. This is z, this is y, this is x. I'll do the z equals 1 minus x squared in blue. I've got a parabola going like that. And in the x equals 0, we got a parabola going like that. So I connect the dots in the plane. The XY plane makes a circle down there. And so we've got kind of like this going on, but more of a parabolic shape. Another way of looking at this is going, well, that's 1 minus x squared plus y squared, which looks like 1 minus r squared. So it looks like a parabola related to the radius. And that's spinning around, so it's not just in one dimension. So getting an idea of what's going on there helps, because that's going to help us do our different stuff. F is what it says. It is literally x in the x direction, y in the y direction, and z in the z direction. So calculating the divergence of F isn't too bad. Remember, we're doing ddx, ddy, ddz of x, y, z. 1 plus 1 plus 1 is 3. So our integral is gonna be triple integral of 3 dv. Now we got to choose how we're going to set up dv. I just got done showing z equals 1 minus r squared, so maybe doing this in cylindrical is easier. Well, so if we do it in cylindrical, 0 is less than r less than 1. Theta is going from 0 to 2 pi. And z is between 0 and 1 minus r squared. Another way to know this is a cup, we did in the past, there was a bunch of different basic graphs we did in 3 dimensions. And parabolas like this paraboloid is one of the shapes we did. So when you have enough practice with it, you start recognizing the paraboloid shapes right away. So we're gonna switch to dz dr d theta. So if I do like the 0 to 2 pi on the outside and then 0 to 1, I definitely need this one on the, this one needs to go first. This has to be before r. Has to, it's absolutely vitally important that we do this one first, or at least before r. We could probably squeeze in theta if we wanted to before that, but z has to be done before r because r is in the limits of integration. The reason why I'm emphasizing it so much is it popped out on the test. Some people, maybe 25% of you on the problem that had that, said, fuck it, I'm going to do it in the opposite order anyways, and ended up with variables in your answer. And you should have had variables. They should have all gone away when you integrated. So my value inside was 3, and then dv, we've got dz, dr, d theta, and then the correction factor for cylindrical is r. So that's my dv right there. And as much as it looks separable right now, it can't be separated yet because z depends on r. Once we deal with DZ, we might be able to separate it because the last two limits of integration have no variables in them. So if I integrate, I got 0 to 2 pi, 0 to 1, 3r, and then z evaluated from 0 to 1 minus r squared. So 0 to 2 pi, 0 to 1, 3r times 1 minus r squared. Let that give you a chance to write that down. At this point, the limits of integration make this separable. I can do 0 to 2 pi d theta. And I can do 0 to 1. I'm going to multiply this out. I've got 3r minus 3r cubed dr. So I've got 2 pi minus 0 times 3 halves minus 3/4 minus 0 minus 0. 3 halves minus 3/4 is 3/4, isn't it?
Yep.
So 2 pi times 3/4 is 3 pi over 2. No variables in the answer. Looks good. I really wish when they were doing mathematics, came up with mathematics, they didn't use theta for the angle. Because theta looks too much like 0. And so often we're doing these integrals, 0 shows up. And I hate having the variable look like one of the limits of integration. I hate theta. B, you don't have that problem. B don't look like anything else.
No, bro.
That looks like.
Or that one, I guess that B does. This one, I like that one.
Seen it like that before. I thought it was something.
Oh.
Like it's. We're seeing this. Like something like this. See, I don't remember what that was. Or maybe it was like this.
That's like everything.
It's a flower.
You guys ready to take a look at another one?
Yes, sir.
I don't know that we'll get finished. Actually, I don't know that we'll get finished on it because it's 10 minutes left, but we can give it a try. Maybe we'll set it up today and have it as a take-home problem. And we'll talk about that, how to, hopefully you guys try to do it on your own after you get home. But maybe look at just setting it up right now. Because I think maybe the hardest part is the setup here.
Are we doing it both ways? Let's do it in this diversion first.
Can't believe you excuse like that, Eric. We're just trying to think.
So just like in the last problem, what's the picture look like? Because this is gonna give us some crazy limits, right? The x squared plus y squared, like we did in the last one, it was a paraboloid going down. This one is a paraboloid going up. So that's that surface.
Oh, you need to cut it off.
No. Oh, that's great.
Now I'm not very good at doing z equals 2x right away. So I'm gonna sketch it in 2D over here and try to map it over to the picture. If I do z and x like that, so this is kind of like y equals 2x. Y equals 2x would be like this, which means z equals 2x looks like that. And this is my positive x direction right here. And that's my positive z direction right there. So I kind of need it coming up like that. And it's a line, and well, the z equals 2x is a line, but this is making a plane. So we got some cup, and there's a slash going through it.
Oh, this is hilarious.
And it cup keeps going up. I put a top to it, but there's no top to it. And apparently there is some slash going through the cup like that. So somewhere that's got to hit. So this should have like some weird shape like this along the.
It's Norman. This, Mr. Jones.
I could tell right away that I could think I want to use cylindrical again. So it's a crazy shape. Let's take a look at the divergence. Let's see what the divergence gives us. Div F. We've got ddx, ddy, ddz. If you are comfortable doing that quicker, please do so. But on the test, like, show this out. Don't just jump to the answer. Show me that you know what the divergence is doing.
Source. It's not a single source. I want to point out there's two more than the 1 point. Guess solve it around, right?
Ah, the divergence of F is 1.
Kind of like the lowest simulation. Kind of like sort of. We need more like current.
Mr. Jones, this is really funny. So I have this exact problem in my notes.
Do you?
Yes, I have this literally the exact same problem in my notes that I'm looking at right now. Where we found the flux of this.
Nice. If I'm looking at this cup, like when X is negative, Z is negative. So on this bowl surface here, fuck. Hey, look good. Okay, did it. Let's do this down below. That thing is kind of like, if I do it from the side, it's doing something like this. This is a side view. So this is Z equals 2X side view, where this is the Y axis coming towards me. And that's X going that way. So I kind of rotated my picture. The point is like, this doesn't have a negative X. So maybe if I shift to cylindrical, Z is going between, the upper one is 2X and the lower one is X squared plus Y squared. In cylindrical, that is R squared is less than or equal to Z, less than or equal to 2R cosine theta. We got to figure out what the radius is. Where it intersects, don't we? So where does that point meet? That meets when the Z's are the same value. So when like 2X equals X squared plus Y squared. Or X squared minus 2X plus Y squared equals 0. And if we complete the square, we get that. Is that helpful? That's not really helpful, is it? That's not a circle centered at the origin. So, where are they meeting? Let me look at it in terms of polar. Where does R squared meet 2R cosine theta? Well, I know R is not, well, R does equal 0 here. It meets down here, but the one I'm worried about is up here. I'm not going to do that. I'm going to not divide by R. We get R times R minus 2 cosine theta. Still isn't really helping, is it? Oh, I know how to get it, find the radius. Well, I'm looking at, I needed to hit when y equals 0. When y equals, let's do that. When y equals 0 is the xy or the xz plane. And that's that point right there when y equals 0. That's the approach to take. So z equals 2x, x squared equals 2x.
Find the boundary.
So x times x minus 2 equals 0. It happens at x equals 2. Which means that happens at z equals 2x at 4. And I need that in terms of a radius. 4 equals x squared plus y squared. The radius is 2. All that to find my r. That was a lot of work to find r, wasn't it? Shit, it's 9:01.
Considering I do have all my notes, I do have an answer if you wanna hear it.
Sure, what's the answer?
I've got pi over 2 for this answer.
Okay, so pi over 2 is what it should boil down to. That's one limit of integration. 0 is less than r, less than 2 is another. And then theta, since we're only doing this part right here, it looks like we're going from negative pi over 2 to pi over 2. This was problem 18 in the book. So if you want to see
I
how,
figured.
I got the.
I figured it was out of the text.
so they might have set it up in spherical. We can go take a look at how they set it up.
I couldn't.
I'll be holding my SI hours today from 1 p.m. to 3 p.m. for anybody that's interested.
Oh, they did. Oh, that was smarter. Oh, it does go off that. Oh, yeah, my R is bad. Because R is changing as I go out. R is 2 cosine theta. I had that right here. Son of a bitch. So R equals 2 cosine theta. See you guys tomorrow.
Yeah, something I'm also noticing with my work compared to yours, that I think Mrs. Harper, she would like set up the integral in rectangular coordinates and then decide to turn it into like cylindrical, spherical. Because that in that particular problem, it was still in rectangular coordinates, and she probably was like, yeah, you can do this at home if you want to, but it turns into this.
I'll take a picture of getting this.
Is that your lunch, pal? That reminds me of, I was in a ceramic class in my sophomore year of high school, and someone had like made this ceramic dish of like French fries, a hamburger, and a soda, and they made it all out of ceramic, and it was even like eggs and stuff. It was really cool. I don't have a picture on my phone.
It would have been a sight to behold.
It was a very great sight. All right, I have nothing on my end, so I'll see you
All right.
tomorrow.
See you tomorrow.